Hi, I am Artem Chubatko and this is Simple Traversals. Simple Traversals is a really good place to start learning about Gremlin. They should be easy to understand because Simple Traversals guide traversers through steps in a sequential order and contain no internal or nested traversals. You can imagine Gremlin, the traverser, this green creature, guided by a simple traversal hopping from one vertex to the next one and to the next one, as shown in this illustration. Let's look at some of the steps we use to define simple traversals. And of course, these steps will be useful in other kinds of traversals as well. They really form a foundation for any of the traversals that we are going to work with. Starting at a vertex, here are some steps we can use to navigate to an adjacent vertex or an incident edge. Out instructs a traverser to move to any adjacent vertex that is connected to our current vertex via an outgoing edge with a matching label. Labels that we passed into out, and all other steps are optional. In tells the traverser to move to an adjacent vertex by traversing an incoming edge. If you do not care about an edge direction, you can use a step called both. You can move to adjacent vertices by traversing edges in any direction. If you want to navigate to an edge, you can use out E, in E, and both E. They work the same as out, in, and both respectively, except they move to an edge rather than a vertex. The reason you want to go to an edge is usually because you want to access edge properties. Of course, a picture always helps when we are talking about graphs. Check this sample graph out. Our traverser, this little gremlin creature, is on the movie vertex right now, and there are various places he can go depending on the step we want to use. For example, out will move the traverser to the genre vertex and the person vertex, and we will end up with two traversers. If instead we use the in step, the traverser will move to the user vertex. Similarly, you can see how the traverser would move if other steps are used. Also, please notice that we are not specifying any labels for these steps in this illustration. This is a valid use case, as labels are always optional. We can always add labels as needed. If our traverser is on the edge, we have a different set of steps that we can use. The out V step is going to move the traverser to the opposite direction of the edge towards the outgoing vertex. In this case, this is a user vertex. In V will move the traverser to the incoming movie vertex. And both V will go to both endpoints of the edge. Finally, the other V step is a bit unique here. It implies that the traverser has some state. Other V will move the traverser to the vertex that was not the vertex that the traverser moved to the edge from. For example, if we move to the edge from the movie, other V will send us to the user. And if we came from the user, other V will direct us to the movie. The graph schema we are going to use for all our examples is based on the killer video domain. In our graph, we have vertices that represent movies, users, genres, and people. These are four types of vertices. They can be related to each other by different types of relationships. Users may know each other and can rate movies. Movies belong to genres. Movies can have actors, directors, composers, screenwriters, and cinematographers. And of course, we have various vertex properties and even one edge property in this schema. User-defined vertex IDs are underlined on the diagram. User-defined vertex IDs are underlined. We have no meta properties, but we do have one multi-property. This is the production property. Please take a moment to study this schema as it will help you to follow all of our traversal examples. Here is our first simple traversal with in step. We want to find titles of all movies with actor Johnny Depp that were released in 2010 or later. We start with the vertex with label person and the name property Johnny Depp. We then traverse incoming actor edges and end up on any movie where Johnny Depp acted in. We further apply the condition for the movie release year. It must be equal or greater than 2010. The final step in the traversal gets the titles of those movies that satisfy the condition. In the output, we see Into the Woods, Pirates of the Caribbean, and Alice in Wonderland. We used this has step a few times already. Now is a good time to take a closer look at has, as this step is very common. We will use it in all types of traversals, not just simple traversals. It turns out that there are several variations of this step that take different parameters. First, there is a test where an element has a certain property key. For example, we may want to check if a vertex has a property title. Second, there is a test for an equality to a particular value. We may be interested in vertex with title Alice in Wonderland. There is a variation with a predicate to test inequalities and more complex conditions. Fourth, you can even have a nested traversal as a test, but we are not going to talk about nested traversals just yet. Fifth, this variation also allows you to include label as part of the test, and you should always use label whenever possible for better efficiency. And so forth. You should spend some time learning about these and other variations that we couldn't fit into this slide. This example uses both in and out step in one traversal. This traversal looks for directors of Johnny Depp's movies released in 2010 or later. You may notice that we took the previous example and made it a bit more interesting. We start with the person Johnny Depp vertex, move to the movie vertices where Johnny Depp acted in, limit the movies to only those that were released in 2010 or later, and lastly, we traverse outgoing director edges using out step to get to people who directed those movies and return their names. We get 3 names, but only 2 of them are distinct. Here, to find user ratings for Johnny Depp's movies released in 2010 or later, we will need to end up on rated edges and retrieve rating values associated with those edges. This is achieved by getting to Johnny Depp's movies from 2010 or later, and then using step in E to get to the rated edges. The result is a bunch of numbers representing user ratings. Now let's learn more about predicates. Some of these are really intuitive and don't require a lot of explanation, like equal, not equal, less than or equal, greater than or equal. Those are usually used to compare values of properties. You can also test equality and inequality of objects in a graph. Inside returns true if the incoming number is greater than the first number and less than the second. Outside returns true if the incoming number less than the first number and greater than the second. Between returns true if the incoming number greater than or equal to the first number and less than the second. Within expects to take a list of 1 or more objects, and it returns true if the incoming object is represented in that list. Without is like the inverse of within, inverse or negation. If the incoming object is not in the list, it returns true. If the incoming object is in the list, without returns false. So far we only used predicates with has step, but there are other steps like where and is that are going to use predicates as well. Keep this list of predicates handy, as they will pop up in many different types of traversals throughout this training. Now let's ask a slightly more interesting question of our movie database. Suppose you want to know how old is a typical user who likes but does not love the Johnny Depp movies made in 2010 or later. That sounds like a complex question. Well, we can do that by again going to the Johnny Depp's person vertex, traversing incoming actor edges to movies, and applying the greater or equal than 2010 predicate on year. Moving on to incoming rated edges and making sure that ratings are either 7 or 8. Jumping to outgoing user vertices and outputting user edges. All steps used in this traversal should be familiar. And even so, we call this traversal simple, it is really quite useful. You will be surprised how many real-life data retrieval problems can be solved using simple traversals. And now, it's time for you to be dangerous. You can do it.